We are now going to start our lecture on a very important topic in statistics. It's probability and its concepts. Now, in statistics, the end goal is to be able to forecast the future, to estimate the unknown, right? To be able to get some grip on the unknown that lies ahead of us, right? Now, there's always a chance that we will not be able to predict the future or predict the unknown accurately, 100% accurately. But we want to be close to what the actual is, right? And that's where probability comes in. Whenever there's an estimation, there is also a play with probability. So we'll go into the details shortly, but this is the introduction to a very, very important topic in probability, which will lead us on gradually to inferential study. At this point, we are completed with the descriptive part of statistics. We are now heading towards, we are not into inferential studies right now, but with this topic, with the probability and its concepts, we are progressing towards inferential statistics. Now, we will be talking about probability over the next few lectures, but in this particular lecture, we are going to introduce the idea of probability, come to know of some concepts behind the probability. Then we'll talk about some terminologies like experiments, events, outcomes, and then go over the process, the formula by which we can calculate probabilities. So what is probability? It is the chance or likelihood of an event or outcome occurring from an experiment. So an experiment can be regarded as the process of trying to estimate or trying to predict or trying to forecast the activity that causes an event to occur. That's what an experiment is. So when we toss a coin, we don't know what the result is going to be. All right, it's completely on chance that it's going to land on its head or on its tail. Now, the process of tossing the coin, which will give us an outcome of head or tail, is called an experiment. If I attempt on predicting the weather 7 days from today, then the act of prediction is the experiment. Now, whether the weather 7 days from today is going to be sunny or it's going to be rainy or it's going to be humid is the event, right? It's the event or the outcome. So we have the experiment, which is an action we take to predict the future, something in the future. And the result of that, the result from the experiment is the event or the outcome. And the likelihood or the chance of a certain event happening is the probability. All right. So when we toss a coin, if we don't know whether it's going to land on its head or tail, correct? So the probability that it's going to land on a head is the chance or the likelihood of it happening from the experiment of tossing a coin, right? Now, probability theory is the science of uncertainty, of course, right? It helps determine the likelihood of a statistical inference to be correct and forms the basis of inferential study. Like we said before, probability is going to lead us onto inferential statistics. So how does it relate to statistics? Because eventually we are going to estimate the population mean based on our sample mean. We will never know what the population mean is going to be really, but we are going to draw an estimation of it. We are going to make an estimation of it based on our sample mean perhaps. And the probability of that being close to whatever the population mean is out there is where probability theory comes in. So what is an experiment? It's an action whose outcome cannot be predicted with certainty. For example, rolling a dice. So when you roll a dice has 6 sides, right? And every side has a unique value on it. So, but we don't know whether it's going to land on a 1 or a 2 or a 6 or a 4. It's a matter of chance. And the process of rolling the dice is an experiment. Spinning the wheel of fortune, right? We don't know where it's going to come and stop. The process of spinning the wheel is an experiment. Drawing a lottery ticket, also an experiment. The event, on the other hand, is some specified result that may or may not occur when an experiment is performed, right? So the example of that would be the roll dice shows a 6, right? So it's an event, a particular event that can occur from rolling a die. It could be a 5, it could be a 6. All of those would be events. Rolling a 1, rolling a 2, rolling a 3. A specific outcome that occurs from rolling a die or tossing a coin, they all represent an event. Now, probabilities are based on what's called an equally likely outcome. That means every event has an equal chance of occurring from an experiment, right? So if our experiment is to toss a coin, right? That's our experiment, toss a coin. And the two outcomes we already know would be a head or a tail, correct? It could either land on its head or it could land on its tail. Each outcome has an equal chance of occurring. So there are two possible outcomes, right? Two possible outcomes. And the coin has one head. So for it to land on its head, it has 1 out of 2 chances. So the probability of a coin landing on its head is 1/2 or 0.5. Likewise, the coin has one tail and a total of 2 possible outcomes. So the probability of the coin landing on its tail is also 1/2. And that's what the equally likely outcome means. It means that every outcome has an equal chance of occurring. If you roll a die, there are 6 possibilities. So let's say now this time our experiment is to roll a die. Roll a die. How many total outcomes are possible from rolling a die? 6 outcomes. There are 6 total outcomes. And out of those 6, each outcome has an equal chance of occurring. So there's only one on the die, on the face of the die, correct? So to roll a 1 is the probability is 1/6. To roll a 2 is 1/6. To roll a 3 is 1/6. To roll a 4 is 1/6. To roll a 5 is 1/6. To roll a 6 is 1/6. And if you add all of them up, 1/6 plus 1/6 6 times is going to give you a total of 1. And that's a special fact that we will learn and come to use later on, that when you sum up all the probabilities from possible probabilities from an experiment, they should all add up to 1 as long as they follow the equally likely outcome rule. And this rule can be quantified using a formula, which is F over N. F meaning the um, F represents the number of ways a certain outcome can occur. Let me write that down here. Well, it's already written, so let's read through it. It says here, an event that can occur in F ways. So F represents the number of ways an event can occur. And N represents the total number of possible outcomes. So might as well write it. F represents the number of ways a particular event can occur. An event occurs. And N represents the total number of events possible. The total number of events possible. So when I use the example on tossing the coin, then N was this 2. The total number of outcomes possible from tossing a coin was 2, either head or a tail. And then F would represent how many ways a head can occur. So if we are trying to calculate the probability of the event that a head would land, that the coin would land on its head, there's only one head on the coin. So it's going to be 1 divided by 2. Number of ways event can occur divided by total number of possible outcomes. Now, many of you may think, or many of you may realize that I have seen this formula before, F over N. Yes, you have. You've seen it when you were calculating relative frequencies from a frequency table. It is the same formula. We just give it a different name this time. We are calculating probability. And F represents, previously F represented frequencies in relative frequency, and N represented the total number of frequencies or sample size. It's the same thing here. We are just defining it slightly differently. F represents, when doing probability, F represents the number of ways an event can occur. We can also consider that as frequency. The frequency with which an event can occur, or number of ways an event can occur, divided by total number of possible outcomes, right? So let's go into this further and try to calculate probabilities from different experiments. Let's look at this example of finding probabilities when we roll a pair of dice. Pair of dice would be rolling 2 dice together. So here we are shown all possible outcomes from rolling. One of them is a red die and the other one is a black die, and we roll them together. Now, if we had rolled just one die, we would have 6 possible outcomes, right, from one die. There would be 6 possible outcomes. However, we are rolling 2 dice together, and possible outcomes from rolling 2 dice is not 6 plus 6, 12, but it's 6 times 6. So when you roll 2 dice, then we get 6 times 6, 36 different combinations. And this is this is with replacement, all right, because the values can repeat after each die, after each roll is what I mean. All right, so we are going to use the F over N rule. So let's do that. F over N. I'm writing the formula here, simple formula. So what is the probability that 11 is rolled? Now n is determined as 36. That will not change no matter what event's probability we are trying to find. N is going to stay 36 for this particular experiment. We have to find f, which is the number of ways this 11 can occur when we roll a pair of dice. So I'm going to go column by column through this display and see which ones have a total, a sum of 11. Now the first column, the highest is 6 plus 1, 7. So there are no 11s here. The second one, 6 plus 2 is 8. Third one, 6 plus 3, 9. So there's no 11 in this column either. In the fourth column, 6 plus 10 is the highest. So no 11s here. Look at the fifth column. The last one is 6 plus 5, 11, right? So I'm going to mark this as 1. All right. One way we got 11. That means when we get a 5 on the red die and a 6 on the a black die. That's one way we can get 11 when we roll the pair. In the last column, let's go through this. 6 plus 1, 7, 8, 9, 10. This one here, the fifth one down the last column, 6 plus 5, 11. This is another way we can get our 11, right? This is the second way. Any other ways? The last one is 6 plus 6, 12. So no, there are two ways in which we can get 11. One is when we get a 5 on the red and 6 on the black. And the other way is we get a 6 on the red and 5 on the black. So there are two possible ways in which we can, or by which we can get 11. So you're going to write for F 2, all right? 2. F is 2, N is 36, so that's 1 over 18. Now you have to use your calculators to compute the value of 1 over 18. It will be an approximate value in decimals, a value between 0 and 1. So you have to write. Probability is not really expressed as a fraction. When you answer probability questions, make sure your final answer is a decimal value, and it should be a decimal value between 0 and 1. It cannot be less than 0. It cannot be greater than 1. All right. This one here, the last one says, what is the probability that doubles are rolled? That means you get the same value on both dice. So let's go through this. Again, F over N is what we are going to apply. F over N, and N is fixed for this experiment. It's going to be 36. We have to see how many different ways we can get the same value, doubles, on both the dice when we roll them. So look at the first one, 1 and 1, same value. So let's circle this one here. The first one itself is one way we can get doubles. Any doubles in the rest of this column? No. Let's look at the second column. It's 2 and 2. So that's another way we can get a double, right? So that's the second way. Then we have in the third column 3 and 3. That's the third way, 4 and 4. So we are going diagonally the way it's arranged. We will just move through it diagonally, as you can figure out, right? 4, then we have 5 and 5. That's a double. So that's the fifth way, and then 6 and 6. That's the sixth way. All right, so there are 6 ways that we can get doubles when we roll a pair of dice. So you're going to write here 6. F is going to be 6. 6 ways we can get a double. So event here is doubles, and the experiment here is rolling a pair of dice. All right. So 6 divided by 36 is 1 over 6. Again, run your calculators through, run this through your calculators to get a decimal value. All right. Okay, so this is one example. We'll go through some other experiments and try to calculate the probabilities. And in the process, we will learn some different facts and different concepts about probabilities. We are now going to discuss what's called the frequentist interpretation of probability. Now, this concept rises from what we just learned about the equal likelihood outcome. Equal likelihood outcome. What does the equal likelihood outcome state? It says that every outcome, right? Every outcome has an equal chance of occurring. An equal chance of occurring. So let's take the experiment of tossing a coin. All right. Now, when we toss a coin, there are two possible outcomes. So let's take our experiment tossing coin. Okay. So it has two possible outcomes, right? That's our N. Two possible outcomes, head or tail, right? We can either get a head or a tail. Now, by the equal likelihood outcome, we would expect, if we start tossing a coin a certain number of times, we would expect 50% of the time for it to land on its head and 50% of the time to land on its tail. Say we toss it 5 times or toss it 10 times, let's say. All right, then we would expect by the equal likelihood outcome that 5 times it'll land on its head and 5 times it'll land on its tail. Right? So in order to validate that, let's say we start tossing a coin. So I'm going to write here the outcomes. Now in the first toss, I'm going to toss it 8 times, right? So first time it lands on the head. All right? Now there is no set pattern of a coin getting an outcome when you toss it, right? There's no set pattern. It's not that because of the equal likelihood outcome, we expect the coin to land on its head. The first 5 times it'll show a head, and then the next 5 times it's going to show a tail, or it's going to alternate one head, one tail, one. It's going to be random, correct? So first time it can be a head. Second time, all right, it can be a tail. Third time it gets a head, but fourth time can also be a head. Fifth time can also be a head. The sixth time, well, it can be a tail. Seventh time it can be a head. Eighth time it can be a head. And you look at this pattern and you wonder what's going on. We were expecting 50% of the time. That means out of 8, we were expecting 4 heads and 4 tails. Instead, we have 7 heads, right? 1, 2, 3, 4, 5, 6. All right, 6 heads, and we have only 2 tails, right? So it's somehow this equal likelihood outcome is not working. What the frequentist interpretation of probability states is that in order for the equal likelihood outcome to be true, you have to repeat your experiment frequently. You have to repeat your experiment. That means toss the coin in this case over and over and over again, not 8 times, not 10 times, not 20 times. You have to keep repeating maybe 100 times, and then you will see that it's even the heads and tails, the outcomes are evening out. All right, it's getting even, in other words, is what I mean to say. All right, so what they did here, they put together 2 computer simulations, for the first one and a second one here, to see the proportion of heads, whether we get 50% of the time. Now 0.5, this is the mark or the probability, the proportion uh, that we should be expecting, all right, from this graph, right? So along the x-axis, we have number of tosses. Along the y-axis, we have the proportion of heads that we are getting. Now you see over here, for 10 tosses, we are way off from the 0.5 mark. Then at 20, we are still, there's quite a gap. All right, it was maybe just about 0.3 when after 30 tosses, then 40 tosses, all right, it's going up, 50 tosses, it's going up, and then from the 60th toss, it was getting closer and closer, and it stays that way. It's pretty close to 0.5 along the 100th toss. All right, so that's what the frequentist interpretation says, and the same thing occurs in this chart. Also in this graph, we see a similar outcome. So the frequentist interpretation of probability states that in order for the equal likelihood outcome to be true, the experiment has to be repeated over and over again frequently, right? Now let's look at some of the basic properties of probability that we may already have realized while we were talking previously about this topic. Now, property 1 says the probability of an event is always between 0 and 1 inclusive. Now, I mentioned this before also, that we use the F over N rule to find probability. That's the equation to calculate probability, but you have to change your fraction to a decimal value. It has to be changed to a decimal value, and when you do that, you have to make sure that you are not less than 0. You don't get a negative value, or you don't get a value greater than 1. If you do, then there must have been a mistake somewhere. You have to go back and check your work. All right, so probability of an event must be a value between 0 and 1 inclusive. So it can be a 0. We can have a probability value of 0. We can have a probability value of 1. But more often we get a value between this range, 0 and 1. Property 2 states the probability of an event that cannot occur is 0. An event that cannot occur is also called an impossible event. Property 3 states the probability of an event that must occur is 1. And that probability, that event, is called a certain event. Let me just give you an example of a situation when we can have a probability value of 0 or a probability value of 1, right? So let's say there is a raffle going on, and there are 100 tickets sold. There were 100 tickets sold, and on a certain date, somebody is going to uh, draw the raffle, and whosoever's name gets picked is going to win a prize, right? Now, out of 100 tickets, if I did not buy a single ticket, I'm not even playing, I didn't purchase a single ticket, all right? What is the probability of my winning a prize? 0, right? Because my name is not in that raffle box. I never purchased a ticket, so there's no chance that my name will get drawn. It's not there in the box. So that is a situation when the probability of my winning the raffle, considering that I didn't even buy a ticket, is 0. It's an impossible event, right? On the other hand, on the other side, if I went and purchased all the 100 raffle tickets, all right, that means all the names in my box, all the tickets in the box have my name on it. what is my probability of winning the raffle? 1, correct? 100% chance I'm going to win because there's nobody else's name in the box. All the tickets carry my name, so whichever ticket gets drawn, I'm going to win, right? That's an example of an event, of a certain event, and in that case, the probability of the event will be 1. It'll have a value of 1. Okay. Now, a terminology used to denote all possible outcomes from an experiment is also called a sample space. So sample space represents the collection of all possible outcomes from an experiment, right? And event, we already know, is a particular outcome, right? A collection of outcomes for the experiment, that is any subset of the sample space, that would be the events. All right, so we shouldn't have to spend too much time on understanding that. We already know what an event is or what a set of events are. But sample space, since you may not be familiar with that term, it represents all possible outcomes from an experiment. We can often represent events using Venn diagrams. In the first box here, what we see is a situation called not E. Not E means, let's say E is defined as a particular event. When we say not E, that means everything else can occur except E. All right, so what they have done here is they have the box represents the sample space or all possible outcomes, and E is a particular event, is one of the events in that sample space. And what they're trying to say is not E means that E does not occur, but all the other possible outcomes can occur, but not E. All right, so that's what not E means. In the second box here in figure B, it's a situation of A and B. All right, so we have an event A and we have an event B. The intersection, that means the common elements of A and that of B, represents A and B. That means both events occur together, A and B. So that's why they have shaded the area of intersection between the two events, A and B. All right. And finally, in this third box, they are trying to show A or B. That means everything associated with event A occurs as well as event B occurs, even the point of intersection. That's A or B. All right, so that explains relationship among events. Another terminology that we must know is called mutually exclusive events. So mutually exclusive events mean either event 1 can occur or event 2 can occur, but they cannot occur together. Both two events or more than two events cannot occur together. They are mutually exclusive. All right. So that's what mutually exclusive events mean. Two or more events are mutually exclusive if no two of them have outcomes in common. There's no commonality. So you can either be absent from class or you can be present in class. You cannot be absent and present at the same time. All right, that those two events are mutually exclusive. Either you are sitting in class or you are not in class. You are absent from class, right? that kind of situation is considered to be mutually exclusive. Here I'm going to go through another example, this time probability calculation from cards. Now, for that, you have to be familiar with a deck of cards. So let me just introduce you here. If you're not familiar with cards, let me just introduce here, talk a little bit about how a deck of cards, what a deck of cards consist of. All right. In a deck of cards, first of all, there are 52 cards in all. Right, let me write that down here. There are total cards, total number of cards in a deck is 52, right? 52. And out of that, there are 4 different suits. What we call here is suits. So you see 4 different patterns. The first one is hearts. The second one is diamonds. We call that diamonds, all right? And then this figure here, like a leaf, a clover leaf, this is called clubs. And then the last one is called spades, all right? So there are 2 red suits and 2 black suits. And the red suits are heart and diamonds, and the black suits are clubs and spades. And each suit has 13 cards, all right? So 4 suits, let me write some information here. 4 suits, 2 red and 2 black, all right? And 13 cards in each suit, 13 cards in each suit. Good. What else? Yes, and there are some face cards here, right? So you see these cards with faces. So each suit has 3 face cards in it. So 3 times 4, in all there are 12 face cards. So let's write that too, 12 face cards, and the rest are non-face cards. Okay, so let's try to answer some of these questions based on a deck of cards. So it's like one of those situations where maybe a magician asks you to draw a card from a pack, right? Without looking. So that's considered to be an experiment. Which card you will draw, nobody knows. All right. So you could draw any one of these cards, and each card is unique. All right. So there's an equal likelihood outcome which is applicable here too. Okay. Probability of an event that a heart is drawn. We are going to use our f of n rule. So probability, and I'm just indicating heart as 8. So probability that we pick a heart, any one of these, which is a heart here. It's the red one here, right? This is the heart. Let me write these suits here. This is heart. This is diamonds. Then we have clubs and spades, right? So there are 52 cards in the pack. So by the f over n rule, we have to figure out what n is. So you could draw any card from this pack. The total number of outcomes is 52. And from that 52, in how many ways can you draw a heart? There are 13 ways we can draw a heart from a total of 52, correct? Any one of these 13 cards would be a heart, correct? So your answer is going to be 13 divided by 52. All right? Which is going to be 0.25. All right, you have to write your probability value in decimal and make sure that your value is between 0 and 1, because we just learned by the first property that probability is a value between 0 and 1 inclusive. Now, next one says event that a king is drawn, right? So probability of a king being drawn. Now, let me just tell you this also. The face cards, there are 3 different face cards in each suit. All right, the one here is king. The first one here, well, let's see, I cannot read. Is it king? Yes, that's the king. No, the first one here after 10 is jack, then queen, and then king. All right, I was not able to read it, but yes, jack, queen, and king. So what is the probability that a king will get drawn? Again, n doesn't change. All right, it's f over n. N doesn't change. N stays as 52. But how many kings are there? There are 4 kings in the deck, right? All these 4. So you're going to say 4 over 52 and then convert this to decimals. Event that a face card is drawn. So probability that a face card is drawn, again f over n rule. N is 52. How many face cards are there here in this? You can count. It's going to be 12. 4 times 3, sorry, 12. So it's 12 divided by 52, whatever the decimal equivalent is. Now we learn about some rules of probability, which is going to make it somewhat easier for us to find the probabilities using some equations, all right, some formulas. So the 3 rules are all based on addition. The first one is special addition rule. Then we have what's called the complementation rule. Complementation rule is really subtraction rather than addition. So we'll talk about that. And then we have the general addition rule. And some of these rules have to do with the relationship between events, 2 or multiple events. The special addition rule is used when we want to find the probability of either one event occurring or the other event occurring. And it's not just for 2 events, it can be used for more than 2 events, multiple events. And the way we write it is the probability of A or B or C and so on. All right, so we can have multiple events. And the formula for that is find the probability of A, find the probability of B, find the probability of C, and so on, and just add them up. All right, so if the question says, or if someone asks you, what is the probability of event A happening or event B happening? All you do is find the probability of A, find the probability of B independently, separately, and just add them. All right. Now, one thing that we must remember is the special addition rule only works for mutually exclusive event. That means either A happens or B happens, right? But there's no intersection between the two. There's no commonality between the events, right? So it will only work for mutually exclusive event. So it says here the special addition rule is used for mutually exclusive event, that is when there is no intersection or overlapping of the events. There cannot be a situation where both A and B can occur at the same time. For that, we will have to use a different rule we'll learn shortly. All right, so again, keep in mind special addition rule used for mutually exclusive events, and all you do is find the probabilities of each event independently and then add them up. Let's look at an example of the special edition rule. A marketing firm is targeting adults aged 60 or older with a new commercial. In order to better serve their client, the firm considers the following. R equals event that the potential customer prefers radio, and T equals the event that the potential customer prefers television. We know the following probabilities. P of R, that means the customers preferring radio, equals 0.28, and the customers preferring television, which is represented as P of T, equals 0.65. Assuming that the events are mutually exclusive, calculate the probability of the event R or the event T occurring. So that means if there is a draw, then what is the probability that you would find a customer preferring radio or a person preferring television, right? So given these probabilities here, it says event R or the event T, all right? So let's go through some notation here. Now, this or is represented as, or the whole probability situation is written out as P of T. Well, we have R first, right? So let's do that. P of R or T. Okay, so probability of R occurring or the probability of T occurring. Now, the special addition rule can only be applied if the events are mutually exclusive. We learned that. And that's why they say over here specifically, assuming the events are mutually exclusive, calculate the probability of the events R and all that. Okay, so P of R or T by the special addition rule, and as long as the events are mutually exclusive, is equal to P of R. That means you have to calculate the probability of R plus the probability of T. All right, so you have to take these individual probabilities given here and then you have to add them up. That will give you the probability of R or T. So that would be probability of R is given to us as 0.28 plus 0.65, which will give you a result of 0.93. Right, that's going to be the probability. Now it has been worked out in the next slide, so let's see if this is the value that they got. One other thing that I want to also point out, that this OR here, all right, is also known as the union of two events. So, and you write that as probability of R union T. This is the notation. This is the notation in set theory for unions. All right. So R union T, which is the same as R or T. So they are used interchangeably. So here they worked out the solution of the problem. It says because these events are mutually exclusive, we can use the special addition rule for mutually exclusive events. The probability of the event of the union of events R and T, again, union is the same as the OR statement. So in brackets, they have the favorite media is either radio or TV, is given by this notation. So they have used this particular notation that I mentioned about in the previous slide. R union T would be P of R plus P of T. So 0.28 plus 0.65 equals 0.93. Now for the most part in this chapter, we are going to refer to this union as R or T. But it's good to be familiar with the set notation also. All right. The next rule that we learn about is the complementation rule. The complementation rule is based on the fact that the sum of all the probabilities, that means the sum of the probabilities of all outcomes from an experiment equals 1. Let me write that down. All right, so the sum of probabilities of all possible outcomes from an experiment is equal to 1. All right. So by the complementation rule, for any event E, the probability of E can be calculated as 1 minus the probability of not E. All right. So in other words, if we have all these events A, B, C, D, E. All right. And I want to find the probability of E. All right. Well, if you know the probability of E, you can just write down whatever it is. The other way is probability of E will be equal to 1 minus probability of A plus probability of B plus probability of C plus probability of D plus probability, and that's it. All right. So 1 minus all the other probabilities will give us probability of E. Now, likewise, since this is like an identity, if probability of E equals 1 minus probability of not E, if the question is, what is the probability of not E? All right, probability of not E will be equal to 1 minus the probability of E. All right. Here's an application of the complementation rule. It says here a random sample of M&M's plain milk chocolate candies was selected. And the following table displays the number of each color of M&M's in the sample. What is the probability of not selecting a brown candy? So there was probably a jar of M&M candies, and M&M candies come in different colors. So the colors here are brown, and there were 91 brown M&Ms and 112. Let me write this more clearly. This is 112. All right. So 112 yellow 112 yellow candies, 102 red, 151 blue, 137 orange, and so on, for a total of 692 candies. Okay, so the question is, what is the probability of not selecting a brown candy? So the probability of not selecting a brown candy would be probability. Remember, what is the probability of selecting a brown candy? Probability of selecting a brown candy would be 1 minus probability of not B's. Correct? Probability of B is 1 minus probability of not B's. So we can use this equation. This time the question is, what is the probability of not selecting a brown candy? So we can work this out like this here. We can do probability of not B is equal to 1 minus probability of B. What they are asking here is, what is the probability of selecting every other color except brown? All right, what is the probability of selecting every other color except brown? What is the probability of not selecting a brown candy? So The probability of selecting a brown candy is 91 over 692, correct? F over n. Here they haven't given you the probability value. You have to calculate it. They've given you the frequency values and n, which is 692. So using f over n, the probability of B is 91 over 692, which comes to a value of 0.1315. So if this is the probability of selecting a brown candy, then the probability of not selecting a brown candy is 1 minus whatever the probability of B is, so 0.1315, which is equal to 0.8685. All right, so this is where complementation rules come in very handy, because it can make the work faster and easier for you. Let me tell you why. If you were to, we could have done it in another way also. We could have found the probability of all the other colors except brown and then added them up. We could have used the special addition rule to solve this. We could have done 112, let's see, 112 over 692 plus 102 over 692 plus 152, what is it, 51 over 692 plus all the way up to 99 over 692, and then done the addition, right? That would be fine, but look at how many probabilities we have to find and then add them up. The complementation rule makes it way more easier. You just find the probability of brown, which is just one probability is what you're calculating, and then subtract that value from 1. All right, because all these probabilities would add up to 1 anyway. Okay, so that's where the complementation rule comes in handy. Now, for events that are not mutually exclusive, we cannot use the special addition rule. For that, we have to use the general addition rule. What is the general addition rule? It says if A and B are any two events not necessarily mutually exclusive, then the probability of A or B happening is the probability of A plus the probability of B minus the probability of A and B. Now, keep in mind, because the events are not mutually exclusive, there could be a point of intersection. There could be a common point. There could be a situation where A and B could occur together, right? So that common intersection has to be subtracted from probability of A plus probability of B, otherwise there will be double counting. And I'm going to work out a problem using the deck of cards and show you why we need to subtract the probability of A and B, the common point between the two events. All right, and again with the set notation, this is how you denote the general addition rule. Probability of C union B equals probability of C plus probability of B minus, now this downturned U symbol suggests intersection. All right, this means intersection of the two events, both events occurring together, and that's the equivalent of and. All right, so the downturned U is and. All right, and the upturned U is or, also called union. This is union, and the downturned U is the intersection, right? Now I'm going to demonstrate the general addition rule using an example of a deck of cards. Let me set up the problem first, which will require an application of the general addition rule. So let's say I want to find the probability of selecting a heart or a face card from a deck of cards. All right. Now, this or suggests that we can go ahead and apply the special addition rule. However, keep in mind the special addition rule only works for mutually exclusive situations, mutually exclusive events. If they are not mutually exclusive events, then we cannot apply the special addition rule. We have to apply the general addition rule. But we first have to figure out whether these events are mutually exclusive or not. All right. Now, what does this special addition rule says? Special addition rule says if there's an OR situation and the two events are mutually exclusive, just find the probability of the first event, find the probability of the second event, and add them. And if there are third or fourth or fifth events, then find each the probability of each event individually and add them all up. That will is what the special addition rule states. The general addition rule states, and I'm going to write it down here at the bottom, the general addition, just a second, the general addition rule says that the probability of A or B, the probability of A or B occurring would be calculated using the formula probability of A plus probability of B, and from that subtract the common events, the probability of the events when probability A and B can occur together. All right, we have to subtract that. So we'll have to see for this particular example of probability of heart or face card, if we have a situation where hearts and face card could occur together at the same time. If that happens, then that means it's not a mutually exclusive situation. We have to subtract the probability of the common of the intersection, commonality of A and B. All right, so let's do our calculations here. Probability of heart or face card, right? So that would be probability of H plus probability of F. So let's try to do the calculations first, and I'm going to start here, perhaps leave some space and start here. All right, equals. Now, what is the probability of finding a heart? Again, we are going to use the formula for probability F over N, correct? That's the formula for finding any probability value. F over N. So what is N in this case? There are 52 cards, unique cards in a deck, and that is going to represent our N, the sample space, the total sample space. So N equals, we know N equals 52, correct? So we have to figure out the F and divide by 52. So probability of a heart, how many hearts do we have here? See, all these values, let's use this. So all these cards here represent hearts, right? These are all the hearts in the deck. All these. How many of them do we have here? 13 hearts. So it'll be 13 over 52. So that's the probability of finding hearts. So 13 over 52. Plus, we have to find the probability of face cards. So how many face cards do we have here? All these cards are our face cards, correct? All these cards. Just a second. Just give me a minute, please. So all these cards are our face cards. All these cards. How many of them do we have here? We have 12 of them. So that's 12 over 52. Now, is there any commonality? Are there any cards that are face cards as well as hearts? That's what we have to look for. That means, can there be a situation where hearts and face cards can occur together? And here we see there are 3 cards where the purple and the yellow intersect, right? The purple and the yellow are intersecting over here. So these 3 cards are hearts as well as face cards. So we have to subtract this common. We have to subtract these 3 cards out of the 52. So minus, so we cannot, this tells us that these are not mutually exclusive events, correct? Because there are situations where hearts and face cards can occur together. So we have to subtract that common intersection, which is probability of hearts and face cards occurring together. And how many of those cards do we have where the cards are hearts as well as face cards? 3 out of 52. So subtract 3 out of 52. And whatever the answer is, 13 plus 12 is 25, minus 3 is 22 over 52. Whatever the calculation comes to is your probability. So this is an application of the general addition rule. All right. So, and whenever the events are not mutually exclusive, then you have to use the general addition rule, where you have to add the probability of the 2 events that we are considering, and then subtract the commonality, the intersection of the 2 events from the probability of A and B. All right. Otherwise, it will cause double counting. Remember, we counted these 3 in probability of hearts. When we were calculating the probability of hearts, we counted these 3, and then when we counted the face cards, we counted those 3 again. So there was a double counting. All right. These 3 cards got double counted, and that's the reason why we have to subtract them from the sum of the first 2 of the 2 events. All right. Now this is the last example in this lecture on general addition rule. It says a concert venue manager needs to gather data on the types of music its patrons enjoy. He gathers data on the following. Event C is the event that a patron enjoys country music, and B is the event a patron enjoys blues. And then data collected were used to estimate the following probabilities. Probability of C equals 0.45, and probability of B, that means that event a person enjoys blues, is 0.22. But they have also given us a situation where a patron enjoys both country music as well as the blues. So this is the point of intersection. The probability that a patron will enjoy country music as well as blues, and that probability is 0.07. So calculate the probability of the union, which also means or. It's the or situation of events C and B, and then which is, in other words, C union B. Again, this is just to familiarize you with the set notation, but you can read it as C or B. Okay, so in the next slide, we will just go over the solutions, but we can actually do the solution here. Might as well do it here. So the question is, we need to find the probability of C or B, but since this is pretty straightforward, they've pretty much given us, they've from this line here, that probability of C intersection B, this downturned U, that tells us that there is a commonality between the two events. So it's pretty straightforward. It'll be equal to probability of C plus probability of B minus probability of C and B, or if we are using the set theory, it's the intersection. All right, so just plug in the values. Probability of C or B will be equal to 0.45 plus 0.22 minus 0.07. All right, so we can just perform this calculation and we will get an answer. So this slide gives us the answer for the problem in the previous slide. Probability of C plus B minus probability of C and B occurring together. Also, this notation read as intersection. So they've added 0.45 plus 0.22 minus 0.07, which is 0.60. All right. Now, this concludes the basics of probabilities and the concepts behind probabilities. In the next lecture, we're going to talk about joint and marginal probabilities and certain other concepts, certain other rules and formulas, and a little more complex probability situations. All right.